Good. We have some time, and therefore I would like to talk a little bit about how Kodo performed over the time and what Kodo can give you. So far we just said, take the coding matrix and bring it together. So here's the practical guide to RLNC libraries, and this is, you have seen the plot in the beginning. That was our very first coding plot on a Series 60 device from Nokia, N95. And at the time, as you can see, we said, okay, what is the throughput in kilobyte per second over the generation size? Even the generation size, we had no idea what is a good generation size. We just put some numbers, right? And what we saw is the more packets we code together, okay, this is like this. Why is this? Even if you have to calculate a bigger matrix, you need more time, right? Nothing else than that. But you see also 2 to the 8 and 2 to the 16, there are some strange effects. For example, at the time, 2 to the 8 had lower than 2 to the 16. We couldn't explain that at the time, had to do with the architecture. But this throughput, like if you take this 40 kilobyte per second, why did we look at network coding in the first place? We wanted to create wireless mesh from telephone to telephone. But the telephones were sending out peer-to-peer 5 megabit per second. Megabit, but mega, okay? So the coding was now the bottleneck. And then I don't need network coding. You know what I would do? I would just repeat my packets and say, come on, I don't care about the coding. Repetition coding is good. I have enough. I'm better. And you will be better in this case. But this was the starting point, and we found it really interesting. And these throughputs were even done with pre-allocated memory. We generated the encoding vectors beforehand, right? We had only the raw encoding. That was even worse. So later you will see when you generate random numbers, it will take time, right? So we said, okay, what can we do here? We had different groups, different student groups. 4th semester, 6, 8, they always do the nice project in Denmark. We say, okay, the main team worked on a new software design. What is a new software design? So you can change the software as it runs. For example, what I told you, shifting the lines, not doing the inverse, but subtracting, multiplying the other. Understanding what kind of impact has your architecture. This is here. Then looking at the right choice of G and F. So binary case results in low complexity. At the time, we did not look at binary. Nobody looked at binary as the case. And Mario Gerla, who was also one from UCLA who looked into network coding, when he saw that we work on binary, he couldn't believe it, how good they are. From the engineering point of view, they are really good. The theory guys, they don't like them. The 1.6 is killing them. Us as an engineer, maybe not. And then we said, why don't we have to do everything in software? Why don't we do hardware in the implementation? Like OpenGL, SIMD, NVIDIA cards, and multi-core, many-core. There's a project here, Dresden Hack, that we used this for 128 Odroids with 1,000 cores, right? Maybe not to do it in the user space, use it in the kernel. But all these were not really good. Yeah? There was not so much that we calculated is factor of 10, maybe a factor of 100 was possible. And then we said, okay, the coding itself, is this the right way we are doing it? We wanted to understand, can we do something better than just take these matrix and fill it up with random numbers? Is there something we can do? And you will learn a little about systematic coding, sparse coding, and optimal prime fields. So we found fields that were 2 to the power of 32 minus 5. This is a prime number, if you don't know. I didn't know. But the math guys, they told us there is a field the security guys are using. And we use this, and you will see something about it. It's a magic number, okay?